Okay, so we're going to talk about the comparison test now as another option for proving if a series converges or diverges. So let's start with this one, the summation from 1 to infinity of 1 over n cubed plus 2. Remember the terms the tests we've talked about. The nth term test, if you took the limit as n went to infinity, you would get 0. That would fail. It's not a geometric series, right? You're not multiplying by the same number to get from one term to the next. Integral test, you could try to integrate 1 over x cubed plus 2. It's possible, but it would really be difficult, so probably not. Now, it looks a lot like a p-series without the 2, right? That would be a p-series with a p-value of 3, which is greater than 1, which means it would converge. And we know as well that when n goes to infinity, this 2 isn't really going to matter very much. So we have good reason to believe that this is going to behave just like the p-series 1 over n cubed. But yet it's not a p-series. So here's how we can work with that, okay? We could note that this particular series, 1 over n cubed plus 2, will always generate terms that are smaller than 1 over n cubed. How do I know that? Well, if we add 2 to the denominator, it's going to make each fraction just a little bit smaller than without the 2, right? And I confirmed here by plugging in some numbers, 1, 2, and 3, and you can tell that every single fraction, 1 for 1, on the left side is smaller than the right side. So we can then use that information. We already know that series is a p-series that converges. And by convergent, remember what we mean. The sum of this series of numbers is a finite number. So what we now know is our series has a sum that is less than whatever this converges to. That's enough to prove that this series converges. And we call this the comparison test, or the direct comparison test we're going to talk about in a few minutes. There's another form of the comparison test called the limit comparison test. If someone just says the comparison test, the default is the direct comparison test, okay? So you'll see the difference when we get to that one. Now, here's another one, n over n squared minus 1. I just made a note here. That is something you could integrate. I think you'd have to, well, you do a u substitution, it wouldn't be too terrible. But it's probably going to be easier to compare this one. As n gets really big, we know in the world of infinities, again, that minus 1 doesn't really matter very much. And n over n squared reduces to 1 over n, which we know is a divergent series. That's the harmonic series. Now, what we could notice here is without the minus 1, that literally equals 1 over n. Putting a minus 1 in the denominator is going to make the denominator smaller, which makes the whole fraction bigger than 1 over n. Now, you could confirm that by writing out terms for both series. Another way you could confirm that is you could take that inequality and cross multiply. We know n's a positive number, so we don't have to worry about multiplying by a negative number and switching the sign. So I get n squared is greater than n squared minus 1. N squareds drop out. And I get 0 is greater than or equal to 1. The way to interpret that, since that's always true, that means that this fraction will always generate fractions bigger than this and this term, this formula. So then we can use that to our advantage. We now could claim that this series is greater than the harmonic series, which we know diverges when p equals 1. Remember, by divergent, we mean the sum of this series is infinity. So we've now shown that our sum of our series is greater than infinity. That means it has to be infinity. It has to be something bigger. Okay. So to be a little more clear then, write this out. With the comparison test, it matters what type of a series you're comparing to. A sub n will be your series, the one you're working on. If you can show it's less than a convergent series, I put C sub n for convergent, then your series would converge too. Conversely, if you can show your series is greater than a divergent series, then your series must diverge as well. The signs are important. If you're comparing to a convergent, you need to be less than, and if you're comparing to a divergent, you need to be greater than. Now, one of the tricky parts you can probably anticipate with this test is, how do I know what to compare my series with? Well, so what we're going to do here is do a bunch of quick examples. I'm not going to run these all the way through, but more about just how would I know what it's comparing to, okay? That's the challenge. So one strategy, which we did on the first two examples, if you have powers of n, is just focusing on the biggest power, right? We know in the big picture, when n goes to infinity, that's what's going to dominate, right? Your n squared is going to be bigger than the 5n. So then if you just reduce that, root n over n squared is really 1 over n to the 3 halves. And it's possible to show that this is less than 1 over n to the 3 halves. That's a convergent p series, right? P is equal to 3 halves, which is greater than 1. You can probably tell why that would have to be true in this case, because once again, without the 5n plus 15, those are equal. This literally does equal that. If n is a positive number, which we're always doing, right? It's usually like 1 to infinity, then this is positive right here. And adding that positive stuff to this fraction makes the whole fraction smaller. Okay. So then we would conclude this one converges too, because it's less than a convergent series. Number 2, same strategy, focusing on the highest power. That's going to behave the same as 1 over n. And you can show that this series is going to be greater than 1 over n. Okay. You can try it for yourself. If you pick a number bigger than 5, okay, again, without that term, those are equal. That equals 1 over n. But if I use numbers bigger than 5, you can tell minus 6 plus 5 is a negative, minus 7 plus 5 is a negative, minus 8 plus 5. So I'm always going to be doing a negative number after the n cubed, which is going to make this whole fraction, well, makes the denominator smaller, which makes the whole fraction bigger. Okay, and since that's a divergent series, ours would diverge too. Okay, one that doesn't have powers of n, 1 over n times 3 to the n. Okay, that would be hard to do any other way here. That would be tough to integrate. And it's not a geometric series because of the n, right? If I didn't have that, that's a geometric series. But notice that would be less than the geometric series 1 over 3 to the n, because I have more stuff in the denominator, right, than this one. That makes this fraction smaller than this one. That's a convergent geometric series with an R value of 1/3. Since our series is less than a convergent series, our series would have to converge too by the comparison test. Okay, inverse tan of n over n squared. Think about what happens as n goes to infinity. You should recall that the inverse tan function as n goes to infinity, I'll put this up here, the limit as n goes to infinity of inverse tan of n is pi over 2. So what that means is inverse tan of n will always be less than, or I guess equal to, pi over 2 over n squared. That's just a constant that could be pulled out of the series. So that means it's pi over 2 times the convergent p series, 1 over n squared, where p equals 2, which is greater than 1, which would show us that this series converges. Okay, how about ln of n over root n? Well, we know that the natural log function is greater than 1 as long as n is greater than e, right? The ln of e is 1, and if you use anything bigger than that, you're going to get a number bigger than 1. So this, if I replace the numerator this time, if I keep the denominator the same, ln is greater than 1, that means this series is greater than the series 1 over root n, which is a p series that diverges. P is equal to 1/2. So that would prove our series is divergent because it's greater than a divergent series. Let's look at some more. Now there's a whole bunch, sorry, make you dizzy here. there we go, that works better, of comparison tests that involve the natural log function. So a really good thing to know about the natural log function, I'm showing you graphically here, and we discussed this when we were doing sequences a while back. If you think about the graph of ln of x, clearly ln of x is less than just x. It's less, it goes to infinity slower than the line y equals x. But somewhat surprising, perhaps, is that the ln function is also less than the square root of x, and the cube root of x, and the fourth root of x, and the fifth root of x. The ln of x, in fact, will always be less than x to any positive power. It's always going to go to infinity slower than x to a power. And we can use this fact to help us through some of these other comparison tests. Okay, number 6, ln of n over n cubed. You absolutely could use the integral test on that one. You would have to do integration by parts, though. That's a long process. But if you knew this, we could make the argument that because ln of n is less than just n, and I keep the denominators the same, and n over n cubed reduces to 1 over n squared, a convergent p-series, well, then we can quickly prove by the comparison test, since our series is less than a convergent series, this would have to converge. Okay, what if we did ln of n is less than n squared, or ln of n over n squared? Now in this case, think about what would happen. Okay, I made the note down here. If we tried to do the same comparison, if we tried to say ln of n is less than n over n squared, that would give us 1 over n, but that's a divergent series, right? And being less than a divergent series doesn't conclude anything, right? If the series is less than infinity, if your series has a value less than infinity, it could be a finite number, sure, but it could also be a smaller version of infinity, which means it could still converge or diverge. That doesn't prove anything. So in this case, we can't use n, but once again, we know that ln of x is less than x to any power, so let's just bring it down a notch. Ln of n is less than root n, and if I use that comparison, that reduces to 1 over 3 halves, 1 over n to the 3 halves, which is a convergent p-series, which means this would converge as well. Okay, these can get kind of involved, okay? 1 over the ln of n, I know that that's greater than 1 over just ln of n. And why do I know that? Is because ln of n is less than n, right? Think about that. If ln of n is less than n, if I take the reciprocal, then 1 over ln of n would be greater than 1 over n, right? So that makes the inside true. And then I could use that same observation to say that 1 over ln of n would be greater than 1 over n. So this whole series is greater than 1 over n, which is a divergent p-series. So I could prove that this one diverges. Okay. All right, so we've run through a few regular comparison tests. There are some drawbacks to the direct comparison test. It has some limitations. So let's look at this one, the series n over n cubed minus 1. We've talked about how to decide what it behaves like if you focus on the highest power, which is 1 over n squared. Now the trouble is that's a convergent series, and we have to then make the claim that our series is smaller than 1 over n squared. But that's not true in this case, right? You can tell because that minus 1 is actually making the denominator smaller, which makes the whole fraction bigger than that. Alternatively, if you do the cross multiplication, you see you end up with the untrue inequality that 0 is less than negative 1. That's telling us that this is a false, that it's not less than, right? In fact, it's greater than. This is greater than 1 over n squared. But the same idea, if you are greater than, if you show your series is greater than a convergent series, meaning the sum of your series is a number, that doesn't prove anything, right? If your series is greater than a number, it could just be a bigger number, which means it converges, or it could be infinity, right? So this doesn't prove anything. This is not useful, okay? So here's what is true. If you look at the biggest power and you realize that it's behaving like 1 over n squared, which is a convergent series, there is no doubt this one will converge. It is going to converge. We just can't use the direct comparison test to make that conclusion, which is why we have the limit comparison test. Okay, so here's how this works. Let's let B sub n be some other series. A sub n is the series we're trying to determine if it converges or diverges. What we do is we take the limit as n goes to infinity of our two sequence parts of our series, our sequence formulas, and that's going to give us some limit. Now, the way I like to think of this, that's like saying a sub n over b sub n approaches L, equals L. So if you cross multiply, that means a sub n is equal to whatever that limit is times b sub n. So now if you think about this, if b sub n is a convergent series, remember convergent series means the sum is a number, right? Sum equals a number. Then what it's saying, if L was a number like 1, 1 times a number is a number. That would prove that our series converges. What if L was a fraction, like a half? A half times a number is a number. That would prove our series converges. What if L is 10? 10 times a number is another number. That would prove it converges. The point I'm making here is, unlike some of the other tests here, L could be lots of different things. It's not limited by 1, except there's one problem here. Included in b sub n, if it converges and it has a sum of a number, what if that number is approaching 0? What if b sub n is a number that's close to 0? You should know from your calculus experience that in the context of limits, if you have 0 times infinity, that's an indeterminate form. So the one thing that L couldn't be in this case to make a conclusion is L can't be infinity, okay? If you're doing the comparing yours to a convergent series. Conversely, let's say that you think your series diverges, so you're doing a limit comparison test with a divergent series, which means, of course, infinity, right? The sum is infinity most of the time. Then this formula is going to be the same, but now you know that b sub n is infinity, right? That has a sum of infinity. So what numbers could L be? Well, L could be infinity this time, right? Infinity times infinity is infinity. But what's the one number L can't be this time is 0 for the same reason. That would give you 0 times infinity. Okay. These are kind of the exceptions. Here's what is true. If you take the limit, if you do the limit comparison test and you take the limit with some other series and you get a number that is not 0 or not infinity, then in either case, what it's telling you is your series is either going to converge if you compared it to a convergent series, or it's going to diverge if you compared it to a divergent series. Okay, let's go back to our example. So we had n over n cubed minus 1. We're going to do a limit comparison test with 1 over n squared, which we know converges. So we take the limit, set up the fraction, we're going to flip. That's going to give us n cubed over n cubed minus 1, which gives us 1. That is L. And remember, for the convergent case, since I'm comparing it to a convergent series, as long as L is not infinity, I can safely conclude now that our series converges by the limit comparison test. Let's do another one. Do one at a time, though. Okay, I have root n over 4n plus 1. I know how to think about what this behaves like by just focusing on the biggest power. Root n over n reduces to 1 over root n, which is a p-series that diverges because my p-value is less than 1. Okay, so again, what I automatically know right off the bat is that I know this diverges, okay? I know it diverges. To demonstrate it, though, I'm going to use the limit comparison test with 1 over root n. So I take the limit of my formula divided by 1 over root n, flip it. That gives me n over 4n plus 1. That limit's going to be 1/4. And remember, for the divergent case, as long as that limit is not 0, then I can safely conclude that our series diverges by the limit comparison test to 1 over root n. Okay. Now, sometimes it's not always apparent what to compare it to. This is no longer powers of n. Okay, and remember, for this one, I would run through all my other tests. If I took the nth term test, 1 over n squared would go to 0, and the sign of 0 is 0, so the nth term test would fail. Sometimes there's hints in the problem. Okay, I see 1 over n squared, which I know is a p-series, right, that converges. So let's see what happens if we do a limit comparison test with 1 over n squared. Take the limit. It's a 0 over 0 limit. You can do L'Hopital's rule. The derivative of sine of stuff is cosine of stuff times the derivative of 1 over n squared, which I didn't work out because I know the derivative of the bottom is going to be the same thing. Those will cancel out. And now if n goes to infinity, you have the cosine of 0, which is 1. Because I compared it to a convergent series, what's important about 1 is it's not infinity. So I can now conclude that our series converges by the limit comparison test with 1 over n squared. One more. Okay, here's another one with ln. Well, I don't know if you could do the integral test on that one, but let's go with the limit comparison test. Sometimes you just gotta get creative. It does what you compare it with. Here's the good news. There's often more than one type of a series you can compare your series with and prove it. It's not just one. The way I would be thinking about this, remember that without that ln, that would be a divergent series, a p-series with p equals 1/2. We even know ln itself is not a very big function. And in fact, I think we just showed on the other page that 1 over ln by itself would diverge. Bottom line is, I'm seeing this whole fraction is not going to get small fast, right? It's not going to generate super small terms really fast. So I suspect it diverges. So then in your head, you'd want to think about, well, what are some series I know that diverge? And one we've used quite frequently has been 1 over n, right? That's your harmonic series, your p series when p equals 1. So if we try that, if we do the limit comparison test with 1 over n, this will flip. And when it flips, right, if you have n over root n, that could reduce to just root n on the top over ln of n. And that will give us, if you do L'Hopital's rule one more time and simplify it, you're going to get infinity. Now, your caution flag should go up here, right? Because remembered, infinity was one of the answers we had to be careful about. But if you go back and look, because we're comparing it to a divergent series, infinity is okay. What would not have been okay is if I had gotten 0. Because I got infinity, which is not 0, then I can conclude that our series diverges with the limit comparison test to 1 over root n. By the way, if you had compared, maybe the first obvious thing here, let me go back to this. Probably the most logical thing here would have been to try to do a limit comparison test with 1 over root n. If you follow through with that and you take your limit, I think what you're going to find out is L would come out to be 0. And that would be a problem. This is a divergent series, and that's the one thing that you're not supposed to get, right? That you can get anything else but 0. So this would not work. I'm going to say test would have failed. Okay, so that's why, if you're wondering why didn't I choose 1 over root n since it was sitting right there, it's because the test would fail with that. So you just go with another divergent series. Okay, I realize, and students over many years get frustrated with both the comparison and the limit comparison test. Understandably, right? Nobody tells you what to compare it with, and oftentimes there's multiple comparisons, right? So they're not the easiest, but with practice, this is why you want to do a lot of problems. You can kind of learn some of the more common comparisons that will work out for you. So I recommend lots of problems from the book. Okay.